The story of the speed of light begins long before scientists had any way to measure it, and even before they knew it was finite. For most of human history, light was assumed to travel instantly. When you opened your eyes, the world appeared immediately. When a fire was lit in the distance, its glow seemed to arrive without delay. This intuitive experience led early thinkers to believe that light had no measurable speed at all, or if it did, it was so fast that it was effectively infinite. This assumption shaped how people understood vision, astronomy, and the very nature of reality. Ancient philosophers debated the nature of light for centuries. Some believed light was a form of emission from the eyes, reaching outward to touch objects. Others believed objects emitted rays that entered the eye. None of these early theories required light to travel over time or distance in a measurable way. It was only with the development of scientific observation and experimentation that the question of light's speed became meaningful. The first major shift in understanding came with the work of early astronomers who carefully observed celestial events. One of the earliest hints that light might have a finite speed came from the study of Jupiter's moons. In the 17th century, astronomers discovered that Jupiter had moons that regularly orbited the planet. These moons would pass behind Jupiter and reappear on a predictable schedule. However, careful observation revealed something unusual. The timing of these events seemed to change, depending on the relative positions of Earth and Jupiter. When Earth was closer to Jupiter, the moons appeared to emerge from behind the planet slightly earlier than expected. When Earth was farther away, the same events appeared delayed. This inconsistency puzzled astronomers until a Danish astronomer named Ole Romer proposed a bold explanation. He suggested that the differences in timing were not due to changes in the moon's motion, but due to the finite speed of light traveling across the varying distances between Earth and Jupiter. Raymer realized that when Earth was farther from Jupiter, light from the moons had to travel a greater distance to reach Earth, causing a delay. When Earth was closer, the light traveled a shorter distance and arrived sooner. By analyzing these differences, he estimated that light took time to travel through space, and he even made one of the first rough calculations of its speed. Although his value was not exact by modern standards, the idea itself was revolutionary. It was the first strong evidence that light did not travel instantaneously. This discovery marked a turning point in physics. It introduced the idea that information from the universe has a finite speed. However, Romer's measurement was only the beginning. Over the next centuries, scientists worked to improve the precision of this value. They developed new experimental methods on Earth to measure light's speed directly. One of the first successful Earth-based experiments was conducted by Hippolyte Fizeau in the 19th century. Fizeau used a rapidly rotating toothed wheel and a beam of light directed toward a distant mirror. The idea was simple but ingenious. Light would pass through a gap in the wheel, travel to the mirror, and return. If the wheel rotated fast enough, the returning light would be blocked by a tooth instead of a gap. By carefully adjusting the speed of rotation and measuring when the light was blocked, Fizeau was able to estimate the speed of light with surprising accuracy. Shortly after, Léon Foucault improved on this method by using rotating mirrors instead of toothed wheels. His experiments provided even more precise measurements and confirmed that light travels much faster than anything else known at the time, but still at a finite speed. These experiments firmly established that light was not instantaneous, but a measurable phenomenon with a definite speed. As experimental techniques improved, scientists continued refining the value of the speed of light. By the late 19th and early 20th centuries, the speed of light in a vacuum had been measured with increasing accuracy. Eventually, it became clear that this speed was not just a property of light itself, but a fundamental constant of nature. The true significance of the speed of light was revealed by Albert Einstein in the early 20th century. Einstein's theory of special relativity fundamentally changed how we understand space and time. He began with two simple but powerful principles. First, the laws of physics are the same for all observers moving at constant speed. Second, the speed of light in a vacuum is constant for all observers, regardless of their motion. This second principle was especially revolutionary. It meant that no matter how fast you are moving, you will always measure the speed of light to be the same. This defied everyday intuition. In normal life, speeds add together. If you throw a ball forward while moving in a train, the ball's speed combines with the train's speed. But light does not behave this way. Its speed remains constant under all conditions. To make sense of this, Einstein proposed that space and time themselves must adjust depending on the observer's motion. This led to two of the most surprising results in physics: time dilation and length contraction. Time dilation means that time passes more slowly for objects moving close to the speed of light compared to those at rest. Length contraction means that objects moving at high speeds appear shorter in the direction of motion. These effects are not just theoretical. They have been confirmed through many experiments, including observations of fast-moving particles and precise atomic clocks placed on airplanes and satellites. The closer an object moves to the speed of light, the more extreme these effects become. From Einstein's theory, it also follows that no object with mass can reach the speed of light. As an object accelerates, its energy increases. The closer it gets to light speed, the more energy is required to continue accelerating it. At the speed of light itself, the required energy becomes infinite. This makes it physically impossible for any massive object to reach or exceed this speed. Only particles with no mass, such as photons, can travel at the speed of light. These particles always move at this constant speed in a vacuum. This is why light from stars travels across the universe at a fixed rate, allowing us to observe distant galaxies as they were in the past. The speed of light is approximately 299,792,458 meters per second in a vacuum. This value is so fundamental that modern physics defines the meter itself based on the distance light travels in a specific fraction of a second. In this way, the speed of light is not just measured, but built into the structure of measurement itself. One of the most important consequences of the finite speed of light is that it limits how quickly information can travel. Nothing in the universe can send information faster than light. This creates a cosmic speed limit that governs all interactions, from atomic processes to the motion of galaxies. Because light takes time to travel, When we observe distant objects in space, we are actually looking back in time. The light from the sun takes about 8 minutes to reach Earth, so we always see the sun as it was 8 minutes ago. Light from nearby stars may take years to arrive, and light from distant galaxies can take millions or even billions of years. This means that telescopes are not just observing space, but also history. The farther we look into the universe, the deeper into the past we see. In a sense, the universe itself is a time machine, allowing us to observe earlier stages of cosmic evolution simply by looking at distant light. The speed of light also plays a central role in defining the structure of causality. Events that are separated by distances that light cannot cross within a given time cannot influence each other. This creates a boundary known as the light cone, which defines the limits of cause and effect in spacetime. Anything outside this boundary is causally disconnected. This structure ensures that the universe has a consistent order of events. Causes always precede effects within the limits set by light speed. Without this limit, the structure of causality would break down, and the concept of predictable physical processes would become meaningless. Even in modern technology, the speed of light is a limiting factor. Communication between Earth and spacecraft, GPS systems, and global networks all depend on signals that travel at or below light speed. Although light is extremely fast on human scales, it still introduces measurable delays over large distances. Despite its importance, the speed of light is not just a technical limitation. It is deeply connected to the structure of reality itself. It links space and time into a unified framework and defines how the universe evolves. It determines how fast information can move, how objects interact, and how we perceive the cosmos. This chapter reveals the speed of light not as a simple measurement, but as a fundamental feature of the universe. It is the boundary between what can and cannot be known instantly, the rule that shapes the flow of time and the structure of space. From ancient observations of Jupiter's moons to Einstein's revolutionary insights, the discovery of light's finite speed transformed our understanding of reality. It is not just a number in physics, it is the ultimate limit that defines the rhythm of the universe itself. After the first realization that light does not travel instantaneously, a new challenge emerged in science. It was no longer enough to know that light had a finite speed. Scientists needed to measure it with precision. But measuring something as fast as light posed a problem unlike anything encountered before. Light crosses Earth's surface in fractions of a second, and over long distances it travels so quickly that ordinary instruments seemed incapable of capturing its motion directly. The task required not only improved tools, but entirely new ways of thinking about measurement itself. In the early stages of this journey, scientists were still limited by mechanical devices. They had no electronics, no lasers, and no atomic clocks. Everything depended on gears, mirrors, and careful observation. Yet even with these limitations, they gradually built a clearer and more accurate picture of light's true speed. Each experiment refined the previous one, narrowing the range of uncertainty and strengthening the conclusion that light has a fixed and universal speed in a vacuum. One of the earliest Earth-based attempts to measure light speed came from the French scientist Hippolyte Fizeau in the 19th century. His approach was both simple and brilliant. He used a rapidly rotating toothed wheel placed in the path of a beam of light. The light passed through a gap between the teeth, traveled to a distant mirror, and then returned back through the same path. If the wheel rotated slowly, the returning light would pass through the same gap, but if the wheel rotated at just the right speed, the returning light would be blocked by the next tooth. By adjusting the rotation speed and measuring when the light disappeared, Fizeau could calculate how long it took for light to travel the distance. This experiment marked a major breakthrough because it brought the measurement of light speed onto Earth itself, rather than relying on astronomical observations. It transformed the problem into a controlled laboratory experiment. Fizeau's results were remarkably close to modern values, considering the limitations of his equipment. His work proved that light speed could be measured using purely mechanical methods, even if those methods required extreme precision. Soon after, Léon Foucault improved upon Fizeau's method. Instead of using a toothed wheel, Foucault used a rotating mirror system. In his setup, a beam of light was reflected off a rotating mirror toward a distant stationary mirror. The light then returned to the rotating mirror, but by that time the mirror had shifted slightly due to its rotation. This small shift caused a measurable change in the angle of the returning beam. By carefully analyzing this shift, Foucault was able to calculate the speed of light with even greater accuracy. Foucault's method had a key advantage. It removed the need for light to pass through physical gaps, reducing mechanical limitations and allowing for more precise control. His results further confirmed that light travels at a very high but finite speed. These experiments gradually moved the scientific community away from any remaining doubts about whether light had a measurable velocity. As experimental techniques improved, scientists began to notice something even more profound. The speed of light did not seem to change depending on the source or direction of the light. Whether light came from a lamp, a star, or a chemical reaction, its speed in a vacuum appeared to remain constant. This consistency hinted that light speed was not just a property of light itself, but a fundamental property of nature. By the late 19th century, the value of the speed of light had been measured with increasing precision. However, a deeper understanding was still missing. Scientists knew how fast light traveled, but they did not yet understand what this speed meant for the structure of space and time. That understanding would soon come from a radical new theory. At the beginning of the 20th century, Albert Einstein introduced a completely new way of looking at the universe. His theory of special relativity was built on two simple principles, but their consequences were extraordinary. First, the laws of physics are the same for all observers moving at constant speed. Second, the speed of light in a vacuum is constant for all observers, regardless of how they are moving. This second principle was especially surprising. It meant that no matter how fast an observer is moving toward or away from a light source, they will always measure the same speed for light. This defied everyday experience, where speeds normally combine. If a train moves forward and a ball is thrown inside it, the speeds add together. But light refuses to follow this rule. It always moves at the same speed, no matter the motion of the observer. To resolve this contradiction, Einstein proposed that space and time themselves must be flexible. They cannot be absolute and fixed, as previously thought. Instead, they must adjust depending on the motion of the observer so that the speed of light remains constant in all reference frames. This idea completely changed the foundation of physics. From this principle came two of the most important concepts in modern science: time dilation and length contraction. Time dilation means that time passes more slowly for objects moving at high speeds relative to a stationary observer. Length contraction means that objects moving at high speeds appear shorter in the direction of motion. These effects are not just theoretical predictions. They have been confirmed in many experiments. For example, particles created in the upper atmosphere by cosmic rays travel toward Earth at speeds close to the speed of light. According to classical physics, these particles should decay before reaching the surface. However, due to time dilation, their internal clocks slow down from our perspective, allowing them to reach detectors on Earth. Similarly, atomic clocks placed on fast-moving aircraft or satellites show slight differences in time compared to identical clocks on the ground. These differences are extremely small in everyday life, but they become significant at high speeds or over long periods of time. This confirms that time is not universal, but depends on relative motion. Einstein's theory also led to a profound conclusion about the nature of energy. As an object with mass accelerates toward the speed of light, its energy increases dramatically. The closer it gets to light speed, the more energy is required to continue accelerating it. At the speed of light itself, the required energy becomes infinite. This means that no object with mass can ever reach or exceed the speed of light. Only massless particles such as photons can travel at this speed. Photons are always in motion at the speed of light in a vacuum. They do not experience time in the same way massive objects do. From their perspective, if such a perspective could be defined, emission and absorption occur instantaneously, even though billions of years may pass in the frame of an external observer. This leads to a strange and counterintuitive picture of reality. The speed of light is not just a limit on motion, it is a boundary that separates different types of physical behavior. On one side are objects with mass, which experience time, acceleration, and inertia. On the other side are massless particles, which always move at light speed and follow entirely different rules of existence. As the understanding of light speed deepened, scientists began to realize that it was not simply a property of electromagnetic radiation, it was embedded in the structure of space-time itself. The speed of light connects space and time into a single unified framework. It defines how distances and durations are related and how events are ordered in the universe. In modern physics, the speed of light is not just measured, it is defined. The meter is defined based on the distance light travels in a specific fraction of a second. This means that the speed of light is fixed by definition, and measurements of space are built upon it. In this way, light speed is not only a physical constant, but also a foundational element of measurement itself. The realization that light has a finite and constant speed also transformed astronomy. Because light takes time to travel, observing distant objects means looking into the past. When astronomers observe galaxies millions or billions of light years away, they are seeing those galaxies as they existed long ago. The universe becomes a layered record of its own history. This also means that the observable universe is limited. There is a boundary beyond which light has not yet had time to reach us since the beginning of the universe. This limit defines the observable horizon. Beyond this horizon, there may be galaxies and structures, but their light has not yet arrived and may never reach us due to cosmic expansion. The speed of light also plays a central role in defining causality. Information cannot travel faster than light, which means that cause and effect relationships are constrained by this speed. Events that are separated by distances too great for light to connect within a given time cannot influence each other. This creates a structure of causal order in spacetime known as light cones. Within a light cone, events can influence each other. Outside of it, they cannot. This ensures that the universe maintains a consistent structure of cause and effect, preventing paradoxes and inconsistencies in physical processes. From early astronomical observations to precise laboratory experiments and revolutionary theoretical insights, the measurement of the speed of light has transformed our understanding of reality. What began as a question about how fast light travels became a discovery about the structure of space, time, and the universe itself. This chapter shows that measuring the speed of light was not just about finding a number. It was about uncovering a fundamental principle that governs everything from the motion of particles to the evolution of the cosmos. The more precisely we measure it, the more deeply we understand the universe it defines. The speed of light was once seen as a measurement problem, something to be calculated with increasing precision. But in the early 20th century, it became something far more profound. It stopped being just a number and became a boundary that reshaped the entire structure of physics. This transformation began with a simple but radical question. What if the speed of light is not just fast, but fundamentally special in a way that defines space and time themselves? Before this shift in thinking, classical physics described a universe where space and time were separate and absolute. Space was a fixed stage where objects moved and time flowed uniformly for everyone, everywhere. In this framework, speeds simply added together. If a train moved at a certain speed and a person walked inside it, their speeds combined in a straightforward way. This matched everyday experience and seemed logically consistent. However, this classical view began to show cracks when scientists studied light more closely. Experiments consistently showed that light did not behave like ordinary objects. No matter how fast an observer moved, they always measured the same speed for light in a vacuum. This was deeply strange because it contradicted the idea that speeds should add together. At first, scientists tried to explain this using the concept of a medium called the ether. They imagined that light waves traveled through an invisible substance filling all of space, similar to how sound travels through air. If ether existed, then light's speed would be constant relative to it, and differences in motion would be explained by movement through this medium. But experiments designed to detect the ether failed. One of the most famous was the Michelson-Morley experiment, which attempted to measure differences in the speed of light depending on Earth's motion through space. If ether existed, light should have traveled at slightly different speeds in different directions. However, the experiment found no such differences. Light's speed appeared constant in all directions. This result created a major crisis in physics. Either the ether did not exist, or the laws of motion and light were far more complex than previously thought. It was at this point that Albert Einstein introduced a completely new framework that removed the need for ether entirely. Einstein began with two simple assumptions. First, the laws of physics are the same for all observers moving at constant velocity. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion. These two principles seem simple, but together they lead to a radical conclusion. Space and time cannot be separate and absolute. They must be connected and flexible. To understand why this is necessary, imagine two observers moving relative to each other. If both measure the speed of light and get the same result, then something else must be changing to compensate for their relative motion. That something is not light, but space and time themselves. From this insight, Einstein developed the theory of special relativity. One of its most surprising predictions is that time is not universal. Instead, time depends on motion. This effect is known as time dilation. A clock moving at high speed relative to an observer will appear to tick more slowly than a stationary clock. This is not an illusion or measurement error, it is a real physical effect. If two identical clocks are separated, and one is placed on a fast-moving spacecraft while the other remains on Earth, they will not agree when reunited. The moving clock will have experienced less time. This effect becomes more pronounced as speed approaches the speed of light. At everyday speeds, the difference is extremely small. But at relativistic speeds, close to light speed, time can slow dramatically. In extreme cases, a traveler moving near the speed of light could experience only a few years, while many years pass in the rest of the universe. Along with time dilation comes another effect called length contraction. Objects moving at high speeds appear shortened in the direction of motion from the perspective of a stationary observer. This means that space itself is not fixed. It changes depending on relative motion, just like time. These two effects, time dilation and length contraction, are not separate phenomena. They are different expressions of the same underlying structure. That structure is space-time, a unified combination of space and time that replaces the classical idea of separate dimensions. In space-time, events are described not just by where they occur, but when they occur. Motion through space affects motion through time. The faster an object moves through space, the more slowly it moves through time. At the speed of light, this relationship becomes extreme. For objects with mass, reaching the speed of light is impossible. As velocity increases, the energy required to continue accelerating increases as well. The closer an object gets to light speed, the more energy it needs. At the speed of light, the energy required becomes infinite, making it unattainable for any massive object. This is not a limitation of technology. It is a fundamental property of the universe. The structure of space-time itself prevents massive objects from reaching or exceeding the speed of light. Only massless particles, such as photons, can travel at this speed. Photons behave in a very different way from objects with mass. They always move at the speed of light in a vacuum, and they do not experience time in the same way massive objects do. From the perspective of relativity, the concept of time along a photon's path becomes undefined in the usual sense, because it always travels at light speed. This leads to a deep insight. The speed of light is not just a limit on motion, it is a limit on causality. It defines how information moves through the universe. No signal, force, or influence can travel faster than light. This ensures that cause and effect relationships remain consistent. If information could travel faster than light, it would be possible for effects to occur before their causes in some reference frames. This would create paradoxes and contradictions in physical law. The speed of light prevents this by enforcing a strict structure of causality known as the light cone. A light cone is a way of visualizing all possible events that can be influenced by or can influence a given event. Inside the cone are events that can be connected by signals traveling at or below light speed. Outside the cone are events that are causally disconnected. This structure preserves the logical order of the universe. Einstein's theory also changed the way we understand energy and mass. It revealed that mass and energy are interchangeable, connected by the famous equation E equals mc squared. This means that mass can be converted into energy and vice versa. It also shows that even a small amount of mass contains an enormous amount of energy. This relationship between mass and energy becomes especially important in high-energy physics and cosmology. In particle accelerators, particles are accelerated to speeds close to light speed, where their energy increases dramatically. In nuclear reactions, small amounts of mass are converted into large amounts of energy, powering stars and nuclear processes. The speed of light also plays a central role in defining how we observe the universe. Because light takes time to travel, looking into space is equivalent to looking into the past. The farther away an object is, the older the light we receive from it. This means that the universe is effectively a time machine, allowing us to observe different stages of its history. When we observe distant galaxies, we see them as they were billions of years ago. We are not seeing the universe as it is now, but as it was when the light left those objects. This gives astronomers a powerful tool for studying cosmic evolution. However, it also introduces a limitation. There is a maximum distance from which light has had time to reach us since the beginning of the universe. This defines the observable universe. Beyond this boundary, there may be more galaxies and structures, but their light has not yet reached us. In addition, the expansion of the universe affects how light travels over cosmic distances. As space expands, light is stretched, increasing its wavelength. This effect is known as redshift. It causes distant galaxies to appear redder and fainter over time, and it provides key evidence for the expansion of the universe. The speed of light is also deeply connected to the structure of fundamental physics. It appears in nearly every major equation describing the universe, from electromagnetism to quantum mechanics to general relativity. It acts as a bridge between different areas of physics, linking them into a unified framework. Despite its name, the speed of light is not just about light. It is the speed at which all massless influences travel. This includes gravitational waves, which were directly detected in recent years. These waves travel at the speed of light, confirming predictions of general relativity and showing that space-time itself can ripple and carry energy. In modern physics, the speed of light is more than just a constant. It is a defining feature of reality. It sets the scale for space, time, energy, and causality. It determines how the universe evolves and how information flows through it. This chapter reveals how a simple observation about light led to a complete transformation in our understanding of the universe. What began as a question about speed became a discovery about the nature of space and time themselves. The speed of light is not just a property of electromagnetic waves. It is a fundamental rule that shapes the structure of everything that exists. Once the speed of light was understood as a fundamental constant that shapes space and time, a new and even stranger consequence emerged. If nothing can travel faster than light, then motion at or near that speed must produce extreme effects on reality itself. These effects are not limited to light or particles. They extend to time, space, energy, and even the structure of causality. This chapter explores what happens when objects approach the ultimate speed limit of the universe, and why, the closer you get to light speed, the more reality begins to distort. To understand these effects, imagine a simple scenario. A spaceship accelerates through space, gradually increasing its speed. At low speeds, nothing unusual happens. The crew inside the ship can walk, talk, and perform experiments just like on Earth. But as the ship's speed increases toward a significant fraction of the speed of light, subtle changes begin to appear. These changes are not caused by mechanical failure or external forces. They are built into the structure of space-time itself. One of the first and most important effects is time dilation. As the spaceship moves faster, time inside the ship begins to pass more slowly compared to an outside observer. If someone on Earth were watching the ship through a powerful telescope, they would see everything on board happening in slow motion. Clocks on the ship would tick more slowly, human movements would appear delayed, and even processes like aging would occur at a reduced rate. Inside the ship, however, everything would feel completely normal. The crew would not notice anything unusual about time. Their biological processes, thoughts, and perceptions would all proceed at the same rate as always. This difference between internal experience and external observation is one of the most counterintuitive aspects of relativity. Time dilation becomes more extreme as the ship's speed approaches the speed of light. At 90% of light speed, the effect is noticeable but moderate. At 99%, it becomes dramatic. At speeds extremely close to light speed, time inside the ship could slow to a crawl relative to the outside universe. A journey that lasts a few years for the crew could correspond to thousands or even millions of years outside the ship. This leads to a fascinating possibility known as relativistic travel. In theory, a traveler moving close to the speed of light could journey across vast distances of space while experiencing only a short amount of personal time. For example, a trip to a distant star system that is hundreds or thousands of light years away could take only a few years for the traveler, while the rest of the universe ages far more. However, this effect does not allow for true faster-than-light travel. It only changes how time is experienced for the traveler. From the perspective of the universe, the ship still moves at less than or equal to the speed of light. The limitation remains absolute. Along with time dilation comes another effect called length contraction. As the spaceship accelerates, distances in the direction of motion begin to shrink from the perspective of the traveler. This is not a physical compression of objects in the usual sense. Instead, it is a change in how space itself is measured. To an external observer, the ship maintains its normal length, but from the perspective of the ship, the distance between its current location and its destination becomes shorter as speed increases. At extreme velocities, interstellar distances could contract dramatically, making distant galaxies appear much closer than they would in a stationary frame. Time dilation and length contraction are not independent effects. They are different expressions of the same underlying geometry of space-time. Together, they ensure that the speed of light remains constant for all observers, regardless of their motion. As velocity continues to increase, another important consequence appears. The energy required to accelerate the ship grows rapidly. In classical physics, adding energy increases speed in a straightforward way. But in relativity, the relationship between energy and speed becomes nonlinear. The closer an object gets to the speed of light, the more energy is required for each additional increase in speed. This is because mass effectively increases with velocity in relativistic terms. While the rest mass of an object remains constant, its relativistic energy increases in a way that makes further acceleration progressively more difficult. As a result, no matter how much energy is applied, the speed of light can never be reached by an object with mass. At the exact speed of light, the required energy would become infinite. This is not a technological limitation, but a structural feature of space-time. It means that the speed of light is not just a high velocity, but a boundary that cannot be crossed. Photons, which are particles of light, always move at this speed. They have no rest mass, which allows them to exist only in motion at the speed of light. From the perspective of relativity, they do not experience time in the same way massive objects do. Their journey through space-time is fundamentally different from anything with mass. This leads to a deeper understanding of what the speed of light represents. It is not simply the speed of light itself, but the speed at which causality and information propagate through the universe. It is the maximum speed at which any influence can travel from one point to another. Because of this limit, the structure of cause and effect is preserved. If signals could travel faster than light, it would become possible for effects to occur before their causes in some reference frames. This would create logical contradictions and break the consistency of physical laws. The speed of light prevents this by defining a structure known as the light cone. Every event in space-time has a light cone that separates possible causal relationships. Inside the cone are events that can influence or be influenced by the event. Outside the cone are events that are causally disconnected. This structure ensures that the universe remains logically consistent even across vast distances and high speeds. It creates a framework in which information flows in a controlled and predictable way. Another important consequence of approaching light speed is the transformation of energy. As an object moves faster, not only does its kinetic energy increase, but its effective mass energy increases as well. This is described by the relationship between energy, mass, and the speed of light. This connection reveals that mass and energy are not separate entities, but different forms of the same underlying quantity. It also shows why even small amounts of mass contain enormous amounts of energy. When matter is converted into energy, as in nuclear reactions, the energy released is proportional to the speed of light squared, a number so large that even tiny amounts of mass produce immense energy output. Relativistic effects also have practical consequences in modern technology. For example, GPS satellites must account for both special and general relativistic effects. Because they move at high speeds relative to Earth and are also in weaker gravitational fields, their onboard clocks run at slightly different rates compared to clocks on Earth. Without correcting for these effects, GPS systems would quickly become inaccurate. On a cosmic scale, relativistic effects shape how we observe the universe. Light from distant objects takes time to reach us, and the expansion of the universe stretches this light as it travels. This means that not only are we seeing distant objects as they were in the past, but their motion and energy are also affected by relativistic and cosmological effects. As objects approach light speed, their behavior becomes increasingly dominated by the geometry of space-time. Motion is no longer simply movement through space. It becomes a combination of movement through space and time. The faster an object moves through space, the slower it moves through time. This relationship reveals a deeper structure of reality. Space and time are not independent dimensions, but are interconnected aspects of a single unified framework. The speed of light defines the conversion factor between them. At everyday speeds, relativistic effects are negligible, but as velocities increase, these effects become dominant. At extreme relativistic speeds, the differences between space and time become so pronounced that classical intuition no longer applies. This is why the speed of light is often described as the ultimate speed limit of the universe. It is not just a limit on motion, but a limit on how space-time itself can be experienced and measured. This chapter shows that approaching the speed of light is not simply a matter of going faster, it is a transformation of reality. Time slows, space contracts, energy increases without bound, and causality becomes tightly structured. The universe itself resists being pushed beyond this boundary. The closer one gets to light speed, the more the universe reveals that it is not built on absolute space and time, but on a flexible and interconnected fabric shaped by this ultimate constant. When discussing the speed of light, it is easy to think of it as a limitation on travel or communication, but in reality, its consequences extend far deeper. The speed of light does not only affect moving objects, it determines how the universe is structured, how space is measured, how time is experienced, and how reality itself is observed. One of the most profound consequences of this cosmic speed limit is that it reshapes how we understand the universe on a fundamental level. To see this clearly, we must step away from the idea of light speed as a number and instead think of it as a boundary built into the fabric of space-time. Every observation we make, every signal we receive, and every image we capture from space is filtered through this boundary. Nothing reaches us instantly. Everything takes time. This simple fact transforms the universe into something very different from what it appears at first glance. When we look at the night sky, we are not seeing the universe as it is right now. We are seeing it as it was when the light left those objects. The moon we see is slightly delayed by about 1 second. The sun is seen as it was about 8 minutes ago. The nearest stars are seen as they were years or decades in the past. Distant galaxies are seen as they were millions or billions of years ago. In a very real sense, the sky is a layered history of the universe. This means that the finite speed of light turns astronomy into a form of time travel. Every telescope is also a time machine. The farther we look, the deeper into the past we observe. There is no way to see the present state of distant objects because their light has not yet reached us. The universe we observe is always slightly outdated, but in a consistent and predictable way governed by light speed. This has profound implications for how we reconstruct cosmic history. When astronomers observe distant galaxies, they are not seeing mature galaxies as they exist today. They are seeing younger versions of galaxies that may have already changed significantly or even ceased to exist in their observed form. This allows scientists to build a timeline of cosmic evolution by observing different distances. Closer galaxies show us the relatively recent universe. Farther galaxies show earlier stages of galaxy formation. Extremely distant observations reveal a time when the universe was still forming its first structures. In this way, light speed allows us to piece together the story of the cosmos from scattered snapshots across time. However, this also introduces a fundamental limit. There is a boundary beyond which we cannot see, no matter how powerful our instruments become. This boundary is not a physical wall, but a horizon defined by the age of the universe and the speed of light. It is called the observable horizon. The observable horizon represents the maximum distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon, there may be galaxies, stars, and structures, but their light has not yet arrived. In some cases, due to cosmic expansion, their light may never reach us at all. This creates a strange situation. The universe may be much larger than what we can observe, but our knowledge of it is fundamentally limited by light speed. No matter how advanced our technology becomes, we cannot observe beyond this boundary. The speed of light sets a hard limit on what is knowable through observation. Another important consequence of light speed is the relationship between distance and simultaneity. In everyday life, we assume that events happening at the same time are universally simultaneous. However, in relativity, simultaneity depends on the observer's motion. Two events that appear simultaneous to one observer may occur at different times for another observer moving relative to the first. This happens because signals used to determine timing also travel at the speed of light. Since information cannot arrive instantly, observers in different states of motion will disagree on the timing of distant events. This leads to the conclusion that there is no universal present moment shared by all observers in the universe. Instead, each observer has their own slice of space-time that defines what they consider to be the present. These slices depend on their motion and position. The idea of a single universal now is replaced by a relativistic structure where time is intertwined with space. This has deep philosophical implications. It suggests that the flow of time is not absolute but relative. What one observer experiences as the present moment may already be the past or future for another observer. The universe does not have a single global clock that governs all events. Light speed is also responsible for shaping the structure of communication in the universe. Because no information can travel faster than light, communication between distant regions is inherently delayed. This means that any exchange of information across space is limited not only in speed, but also in simultaneity. In practical terms, this is why communication with spacecraft becomes increasingly delayed as they move farther away. Signals sent to Mars take minutes to arrive, and signals sent to distant probes in the outer solar system can take hours. For interstellar distances, communication delays become so large that real-time interaction becomes impossible. On even larger scales, communication between stars or galaxies is effectively frozen from a real-time perspective. Civilizations separated by light years would experience communication delays that span generations. This creates a universe where coordination across vast distances is fundamentally limited. The speed of light also plays a crucial role in the expansion of the universe. As space expands, distant galaxies move away from each other. This expansion affects how light travels through space. Light emitted from distant galaxies is stretched, increasing its wavelength and shifting it toward the red part of the spectrum. This phenomenon is known as redshift. Redshift provides one of the strongest pieces of evidence for the expanding universe. It shows that space itself is stretching over time, carrying galaxies apart. The farther away a galaxy is, the faster it appears to be receding from us. This relationship between distance and velocity is directly tied to the structure of space-time and the speed of light. However, cosmic expansion introduces another surprising effect. There are regions of the universe that are moving away from us faster than light due to the expansion of space itself. This does not violate the speed of light limit because it is space that is expanding, not objects moving through space. Still, it creates a horizon beyond which galaxies recede too quickly for their light to ever reach us. This leads to the concept of a cosmic event horizon. Beyond this horizon, regions of the universe are permanently inaccessible. Even though those regions exist, their light will never arrive because space expands faster than the light traveling through it. This means that parts of the universe are forever hidden from observation. Light speed also determines how gravity behaves across space. According to general relativity, changes in gravitational fields propagate at the speed of light. This was confirmed with the detection of gravitational waves, ripples in space-time produced by massive cosmic events such as black hole collisions. These gravitational waves travel through the universe at light speed, carrying information about their sources. Their detection confirmed that space-time is not static, but dynamic, capable of bending and oscillating. It also reinforced the idea that the speed of light is a universal limit for all forms of information transfer, not just electromagnetic radiation. On the smallest scales, light speed influences how particles interact. In quantum field theory, particles interact by exchanging force carriers that propagate at or below light speed. This ensures that even at the quantum level, causality is preserved. The speed of light therefore acts as a unifying principle across all scales of physics. It governs the behavior of particles, the structure of atoms, the dynamics of stars, and the evolution of the universe itself. It connects quantum mechanics, relativity, and cosmology into a single framework. One of the most striking consequences of light speed is that it limits knowledge itself. Because information cannot travel faster than light, there are regions of the universe that are fundamentally unknowable to us. No matter how advanced our instruments become, we can only observe what has had time to reach us. This means that our picture of the universe is always incomplete. It is not just limited by technology, but by the structure of reality itself. The speed of light creates a boundary between the observable and the unobservable universe. Despite this limitation, the finite speed of light also gives structure to our understanding. It allows us to reconstruct history, define causality, and measure distances in a consistent way. Without it, the universe would be fundamentally chaotic, with no clear order of events. This chapter shows that the speed of light is not just a property of motion, but a deep organizing principle of the cosmos. It shapes how we see the universe, how we understand time, how we define space, and how we interpret reality itself. Every observation we make is shaped by its finite value. Every image of the cosmos is a record from the past. Every boundary of knowledge is defined by it. The speed of light is not just a limit on how fast things can move, it is the limit that defines what it means to observe, to know, and to understand the universe. The idea that nothing can travel faster than light is one of the most famous principles in physics, but it is also one of the most misunderstood. At first glance, it sounds like a simple rule about speed. However, in reality, it is not just a statement about motion. It is a statement about the structure of space-time itself, about energy, causality, and the fundamental limits of what the universe allows. To understand why this limit exists, we must go beyond intuition and examine what happens as an object approaches the speed of light. In everyday life, increasing speed is straightforward. If you push an object harder, it moves faster. If you continue applying force, it continues accelerating. This works perfectly well for cars, airplanes, and even rockets at low speeds compared to light. But as speeds increase and approach a significant fraction of the speed of light, this simple relationship begins to break down. The rules of classical physics no longer apply in the same way. Instead, relativistic effects begin to dominate, and the relationship between force, energy, and velocity changes fundamentally. One of the key reasons nothing can reach or exceed the speed of light lies in how energy behaves at high speeds. In classical physics, kinetic energy increases smoothly with velocity, but in relativity, energy increases in a non-linear way. As an object moves faster, more and more energy is required to continue accelerating it. This increase is not gradual in a simple sense. It grows rapidly as the object approaches the speed of light. The closer the velocity gets to this limit, the more energy is required for each additional increase in speed. This relationship is described by the Lorentz factor, which grows without bound as velocity approaches light speed. At low speeds, the Lorentz factor is nearly equal to 1, meaning relativistic effects are negligible. But as speed increases, the factor grows dramatically. Near the speed of light, it approaches infinity. This means that the energy required to reach the speed of light also approaches infinity. This is the core reason why no object with mass can reach the speed of light. It is not because of technological limitations or engineering challenges, it is because the structure of space-time itself prevents it. No finite amount of energy can achieve what would require an infinite amount. To understand this more deeply, it helps to think about what speed actually means in relativity. Speed is not just movement through space, it is movement through space-time. Every object in the universe is always moving through space-time at a constant combined rate. If an object is stationary in space, it moves entirely through time. If it moves faster through space, its motion through time slows down. At the speed of light, this relationship reaches an extreme limit. Massless particles, such as photons, move entirely through space and not through time in the usual sense. They always travel at the speed of light and do not experience time in the way massive objects do. Massive objects, however, must always divide their motion between space and time. This is what prevents them from reaching the speed of light. As they accelerate through space, their progression through time slows down, but it can never stop completely. Reaching light speed would require time to stop entirely, which is not physically possible for objects with mass. This is why the speed of light is often described as a boundary between different types of existence in space-time. On one side are massive objects that move through both space and time. On the other side are massless particles that move only through space at the maximum possible speed. Another important aspect of the light speed limit is its role in preserving causality. Causality is the principle that cause must always precede effect. This is fundamental to the structure of logic and physical law. If information could travel faster than light, this principle would break down in certain reference frames. To understand this, consider two observers moving relative to each other. If a signal was sent faster than light from one point to another, different observers could disagree on the order of events. In some frames of reference, the effect could appear to occur before the cause. This would lead to paradoxes, where information could be received before it was sent. Such situations would make the universe logically inconsistent. Physical laws would lose predictability, and the concept of cause and effect would break down. The speed of light prevents this by ensuring that no information can travel fast enough to violate causal order. This is why light speed is often described as the speed of causality itself. It is not just the speed of light or electromagnetic waves, but the maximum speed at which any influence can propagate through the universe. This includes not only light, but also gravitational effects, quantum interactions, and any form of signal or information transfer. Another way to understand the light speed limit is through space-time geometry. In relativity, every event in the universe can be represented in a four-dimensional structure called space-time. Within this structure, the speed of light defines a fundamental boundary called the light cone. The light cone separates all possible events into three categories. Events inside the future light cone can be influenced by the present event. Events inside the past light cone can influence the present event. Events outside the light cone are causally disconnected and cannot influence or be influenced within the limits of light speed. This geometric structure ensures that information flows in a consistent and ordered way. It defines what is physically possible in terms of communication and interaction. Anything outside the light cone is effectively unreachable within the constraints of the universe. Even gravity respects this limit. Although gravity was once thought to act instantaneously, we now know that changes in gravitational fields propagate at the speed of light. This was confirmed by the detection of gravitational waves, which are ripples in space-time produced by massive accelerating objects such as merging black holes. These waves travel at light speed, carrying information about their sources across the universe. Their detection confirmed that space-time itself is dynamic and that changes in its structure cannot propagate faster than light. The light speed limit also appears in quantum field theory, which describes the behavior of fundamental particles and forces. In this framework, particles interact by exchanging force carriers that travel at or below the speed of light. This ensures that even at the smallest scales, causality is preserved. Interestingly, while no object or information can travel faster than light, there are situations where certain effects can appear to exceed this limit without violating physics. For example, in some wave phenomena, the phase velocity of a wave can exceed the speed of light. However, this does not carry information or energy faster than light, and therefore does not violate relativity. Similarly, in certain quantum entanglement scenarios, correlations between particles appear to be instant. However, these correlations cannot be used to transmit information faster than light. The underlying structure of quantum mechanics still respects relativistic causality. There are also speculative ideas in physics that explore ways around the light speed limit, such as warp drives or wormholes. These concepts suggest that space-time itself could be manipulated in such a way that effective, faster-than-light travel becomes possible. However, these ideas require exotic conditions or forms of matter that have not been observed, and they remain purely theoretical. In a warp drive scenario, space in front of a spacecraft would contract, while space behind it would expand, allowing the craft to move effectively faster than light without locally breaking the speed limit. In a wormhole scenario, two distant points in space-time could be connected through a shortcut. But both ideas face major physical and practical challenges. Even if such structures were possible, They would not violate the local speed of light limit. Instead, they would exploit the geometry of space-time itself. Locally, nothing would exceed light speed. The structure of space-time would simply allow for unusual global paths. This reinforces an important idea. The speed of light is not just a limit on motion through space, it is a constraint on the geometry of space-time itself. It defines how distances, durations, and causal relationships are structured across the universe. Another consequence of this limit is that it creates a fundamental separation between what can be known and what cannot. Because information cannot travel faster than light, there are regions of the universe that are permanently inaccessible to us. These regions exist beyond our cosmological horizon, and no signal from them can ever reach us. This means that the universe is not fully observable in principle. There are parts of reality that are beyond not only our current reach, but any possible future observation. The speed of light ensures that knowledge has a boundary. Despite this limitation, the speed of light also provides structure and predictability. It allows the universe to function in a consistent way, where events unfold in a logical sequence and information flows in a controlled manner. Without it, causality would break down, and the universe would become fundamentally unpredictable. This chapter shows that the light speed limit is not a restriction imposed by technology or energy alone. It is a deep structural feature of reality. It arises from the geometry of space-time, the nature of energy, and the requirement that causality remains consistent. Nothing can travel faster than light, because doing so would require breaking the fundamental structure of the universe itself. The speed of light is not just a limit, it is a rule that defines how reality is built. Light is often treated as something ordinary in daily life, something that simply allows us to see the world around us. But on a cosmic scale, light is far more than illumination. It is the primary messenger of the universe. Every piece of information we have about distant stars, galaxies, and the early universe itself arrives through light or signals that travel at the same ultimate speed. Without it, the universe would be silent, invisible, and fundamentally unknowable beyond our immediate surroundings. To understand the role of light in the cosmos, we must first recognize that light is not just a phenomenon that exists within the universe, it is the medium through which the universe reveals itself. Every telescope, every observation, and every image of deep space is built upon photons that have traveled across vast distances and enormous stretches of time before reaching us. When we observe a star, we are not seeing the star as it is at this exact moment. We are seeing it as it was when the light left its surface. Because light travels at a finite speed, every observation is delayed. This delay is not a flaw in our instruments. It is a fundamental property of reality. For nearby objects like planets in our solar system, this delay is small. The light from the moon takes just over 1 second to reach Earth. The sun's light takes about 8 minutes. But as we look deeper into space, these delays grow dramatically. Light from nearby stars may take years, and light from distant galaxies can take millions or even billions of years to arrive. This means that astronomy is inherently a study of the past. The farther we look, the further back in time we see. In a very real sense, the universe acts as a vast archive of its own history, with light carrying snapshots of different eras across cosmic distances. One of the most important consequences of this is that we can observe the evolution of the universe over time. When we look at nearby galaxies, we see them in relatively modern states. When we look farther away, we see galaxies in earlier stages of formation. At even greater distances, we observe a universe that was still forming its first structures. This layered structure of observation allows scientists to reconstruct the history of the cosmos. It is as if different regions of space act as pages in a book, each page showing a different chapter in the universe's evolution. Light is what allows us to turn those pages. However, light does not simply travel through space unchanged. As the universe expands, the light traveling through it is stretched. This stretching increases the wavelength of light, shifting it toward the red end of the electromagnetic spectrum. This phenomenon is known as redshift. Redshift is one of the most important tools in cosmology. It provides direct evidence that the universe is expanding. The farther away a galaxy is, the more its light is redshifted, indicating that space itself is stretching between us and that galaxy. This relationship between distance and redshift allows scientists to measure the expansion rate of the universe. But redshift also means that the light we receive from distant objects carries the imprint of cosmic expansion. It is not just a record of where the object was, but also of how the universe has changed during the time the light was traveling. Light becomes a record of both space and time. As we look even deeper into the universe, we reach a point where light comes from a time when the universe was very young. This is the cosmic microwave background, a faint glow that fills the entire sky. It is the oldest light we can observe, originating from a time when the universe was only about 380,000 years old. Before this time, the universe was too hot and dense for light to travel freely. Photons were constantly interacting with charged particles, making the universe opaque. Once the universe cooled enough for atoms to form, light could finally travel freely through space. That ancient light is still traveling today, stretched into microwave wavelengths by billions of years of expansion. The cosmic microwave background is one of the most important pieces of evidence for the Big Bang model. It shows that the universe was once in a hot, dense state and has been expanding and cooling ever since. It also provides a snapshot of the early conditions that eventually led to the formation of galaxies, stars, and planets. Light also defines the limits of what we can observe. Because the universe has a finite age, and light travels at a finite speed, there is a maximum distance from which light has had time to reach us. This boundary is called the observable universe. The observable universe is not the entire universe. It is only the region from which light has had time to reach Earth since the beginning of cosmic expansion. Beyond this region, there may be far more galaxies and structures, but their light has not yet reached us and may never do so. This creates a fundamental limit to observation. No matter how powerful our telescopes become, we cannot see beyond this boundary. It is not a technological limitation, but a physical one imposed by the speed of light and the age of the universe. Another important role of light in the cosmos is its connection to energy and matter. Light carries energy across space, and when it interacts with matter, it can transfer that energy. This is how stars shine, how planets receive heat, and how biological systems on Earth ultimately receive energy from the sunday. Inside stars, nuclear fusion produces enormous amounts of energy in the form of light and other radiation. This light slowly makes its way from the core of the star to its surface, where it is emitted into space. The journey of photons inside a star can take thousands or even millions of years before they finally escape. Once released, this light travels through space at the speed of light, carrying energy outward across the universe. Some of it eventually reaches planets like Earth, where it drives weather, climate, and life itself. Without light, there would be no energy transfer across cosmic distances. Light also plays a key role in determining the structure of matter in the universe. When atoms absorb or emit light, they do so at specific wavelengths. These patterns allow scientists to determine the composition of distant stars and galaxies. By analyzing light spectra, we can identify elements that exist billions of light years away. This process, known as spectroscopy, allows us to study objects we cannot physically reach. Light becomes a tool for remote sensing of the universe. It carries information about temperature, motion, composition, and even magnetic fields across vast distances. In addition, light is deeply connected to the structure of space-time itself. According to relativity, light always travels along paths called null geodesics. These paths represent the shortest possible route through space-time for massless particles. They define the geometry of how information moves through the universe. Because light follows these paths, it helps define the structure of causality. Events connected by light signals are part of each other's causal past or future. Events not connected by light are causally separated. This reinforces the idea that light speed is not just a property of photons, but a fundamental feature of space-time geometry. On a more practical level, light is also what allows us to construct maps of the universe. Every image of a galaxy cluster, every deep field observation, and every cosmic survey is built from photons collected over long periods of time. These photons carry information about distance, motion, and structure. Even phenomena that are not directly visible, such as black holes, are studied through light. Although black holes themselves do not emit light, their surroundings often produce intense radiation. Accretion disks, jets, and gravitational lensing effects all produce observable light that reveals the presence of these invisible objects. Gravitational lensing is particularly important. Massive objects like galaxies can bend the path of light passing near them, acting like cosmic lenses. This bending allows us to see distorted or magnified images of distant objects. It also provides evidence for the presence of dark matter, which does not emit light but affects its path through gravity. Light is therefore not only a messenger of what exists, but also a probe of what cannot be seen directly. It reveals hidden structures, invisible matter, and distant regions of the universe that would otherwise remain unknown. As we extend our observations further into space, we are also extending them further back in time. Because of the finite speed of light, the universe becomes a layered structure of history. Every direction we look contains information from a different era of cosmic evolution. This leads to a profound realization. The universe is not static in our observations. It is dynamic and time-dependent. What we see is always a combination of distance and history, shaped by how long light has been traveling to reach us. Light also imposes a limit on how quickly we can learn about changes in the universe. If a distant star explodes, we will not know about it until the light from that explosion reaches us. This delay can be millions of years. In this way, the universe can change without our immediate knowledge. Despite this limitation, light remains the most powerful tool we have for understanding the cosmos. It connects us to the farthest reaches of space and the earliest moments of time. It carries the story of the universe across unimaginable distances. This chapter shows that light is not just a physical phenomenon, but the fundamental bridge between the universe and our understanding of it. Without its finite speed, there would be no cosmic history to observe, no structure to map, and no way to reconstruct the evolution of everything we see. The speed of light does not only limit motion, it defines how the universe reveals itself across space and time. The universe we observe is not infinite in what we can see, even if it may be infinite in size. This limitation is not caused by the size of our instruments or the strength of our telescopes. It is caused by something far deeper and more fundamental. The speed of light, combined with the finite age of the universe and its continuous expansion, creates boundaries that define what is and is not observable. These boundaries are known as cosmic horizons, and they represent one of the most profound consequences of light having a finite speed. To understand cosmic horizons, we must begin with a simple idea. Because light takes time to travel, there is always a delay between an event occurring and us observing it. The farther away the event is, the longer the delay. This delay is manageable within our solar system and even within our galaxy, but on intergalactic scales it becomes enormous. Eventually, we reach distances where light has not yet had enough time to reach us since the beginning of the universe. This creates the first important boundary, the particle horizon. The particle horizon defines the maximum distance from which light emitted since the beginning of the universe has had time to reach an observer. Everything within this horizon is observable in principle. Everything beyond it is currently unobservable because its light has not had enough time to arrive. This means that the observable universe is a sphere centered around the observer, defined not by physical walls, but by time and the speed of light. As time passes, this horizon expands, because light from more distant regions has had more time to reach us. In this sense, the observable universe is constantly growing. However, there is another layer of complexity. The universe is not static. It is expanding. Space itself is stretching, carrying galaxies away from each other. This expansion changes how light travels across cosmic distances. It is not simply a matter of light moving through fixed space. Instead, the space itself is changing while the light is in transit. Because of this expansion, there is a second and more subtle boundary called the event horizon of the universe. This horizon defines the limit beyond which events occurring today will never be observed, even in the infinite future. This is different from the particle horizon, which is about what we can see now. The event horizon is about what we can ever see. The existence of this horizon is tied to the accelerated expansion of the universe. Observations show that the expansion of the universe is not slowing down due to gravity, as once expected, but is instead accelerating. This acceleration is attributed to a mysterious component called dark energy. As space expands faster and faster, distant regions of the universe begin to recede from us at increasing speeds. In some cases, the expansion of space becomes so strong that it effectively carries galaxies away faster than light can travel toward us. This does not violate the speed of light, because it is space itself that is expanding, not objects moving through space. But the consequence is that light emitted from those regions may never reach us. This leads to a strange and profound conclusion. There are galaxies that exist today whose light will never reach Earth, no matter how long we wait. They are effectively beyond our causal reach. Even though they are still part of the universe, they are separated from us not by distance alone, but by the dynamics of space-time itself. Over time, more and more regions of the universe will cross this event horizon. From our perspective, distant galaxies will gradually fade away, not because they disappear, but because their light becomes increasingly redshifted and stretched. Eventually it will become so stretched that it is no longer detectable. These galaxies will seem to vanish from the observable universe. This creates a future universe that is very different from the one we observe today. If we imagine an observer billions of years in the future, they may see a much smaller and more isolated cosmic environment. Many of the galaxies we see today will no longer be visible to them. Their observable universe will be more limited, not because the universe has shrunk, but because the horizons have shifted. The existence of cosmic horizons reveals something fundamental about the nature of knowledge in the universe. There are limits to what can be known, not because of ignorance or lack of technology, but because of the structure of space-time itself. The speed of light enforces these limits. Another important consequence of cosmic horizons is that they divide the universe into causally connected and causally disconnected regions. Within the observable universe, events can influence each other through light or other signals. Outside the horizon, regions are permanently disconnected from us. No signal from those regions can ever reach us, and no signal from us can ever reach them. This separation creates a patchwork structure of the universe, where different regions evolve independently once they cross each other's horizons. In a sense, the universe becomes fragmented into domains of causality, each limited by the speed of light and cosmic expansion. Despite these limits, cosmologists can still study the large-scale structure of the universe using the light that does reach us. By observing distant galaxies, cosmic background radiation, and large-scale distributions of matter, scientists can reconstruct the history and geometry of the observable universe. One of the most important tools in this reconstruction is the cosmic microwave background. This faint radiation comes from the early universe, long before galaxies formed. It represents the farthest light we can observe in any direction. It is effectively the edge of the observable universe in time, a snapshot of the universe when it first became transparent to light. The cosmic microwave background also defines a kind of surface in space, often referred to as the surface of last scattering. This is not a physical surface, but a boundary in time and space where photons last interacted with matter before traveling freely across the universe. It provides a detailed map of the early universe and its initial conditions. Beyond this surface lies a region of the universe that is opaque to direct electromagnetic observation. We cannot see beyond it using light because the universe was not transparent at that time. This is another form of observational horizon, separate from but related to the cosmic event horizon. Together, these horizons shape our entire understanding of the cosmos. They define what we can observe, what we can infer, and what will forever remain hidden from us. They are not obstacles created by instruments, but fundamental features of reality. The speed of light is at the core of all these boundaries. Without a finite speed for information, there would be no delay between distant events and observation. The universe would be immediately visible everywhere at once. But because light travels at a finite speed, the universe is revealed gradually, layer by layer, in both space and time. This gradual revelation creates a kind of cosmic horizon effect, even on smaller scales. Even within galaxies, we only see events after light has had time to travel. We never observe anything instantaneously. Every observation is a delayed reconstruction of reality. Another subtle consequence of cosmic horizons is that they limit our ability to test certain theories about the universe. If regions beyond the horizon contain different physical conditions or structures, we may never be able to verify them directly. This introduces a fundamental limit to empirical science on the largest scales. For example, if the universe contains regions with different physical constants or laws, those regions may lie beyond our observable horizon. In such cases, we would have no direct way of confirming their existence. We could only infer their possibility through theoretical models. This raises deep philosophical questions about the nature of scientific knowledge. If parts of the universe are permanently unobservable, then our understanding of reality is necessarily incomplete. We are always working within a limited observational window defined by light speed and cosmic expansion. Even so, the regions we can observe are vast beyond imagination. The observable universe contains billions of galaxies, each with billions of stars. Within this vast structure, light has carried information across billions of years, allowing us to reconstruct an intricate history of cosmic evolution. Yet even this vast observable domain is only a fraction of the total universe, assuming the universe extends beyond our horizon. The true size of the universe may be infinite or simply much larger than what we can see. We do not currently know. Cosmic horizons also influence the future of astronomy. As expansion continues, more regions will cross beyond our event horizon. Distant galaxies will fade, and the observable universe will become more isolated. In the far future, observers may only see a small local group of galaxies, with everything else lost beyond the horizon. This creates a dynamic universe where observability itself changes over time. What is visible today may not be visible in the future, and what is invisible today may never become visible. This chapter reveals that the speed of light does not only limit how fast we can travel or communicate, it defines the very boundaries of observation and knowledge. It creates horizons that separate what can be seen from what is forever hidden. The universe is not fully open to observation. It is divided by light speed into regions of visibility and invisibility, past and future, connection and isolation. These cosmic horizons are not just abstract concepts, they are the edges of what it means to observe reality itself. Throughout the history of physics, the speed of light has stood as one of the most firmly established limits in nature. Every confirmed experiment, every tested equation, and every observation across the universe agrees on the same conclusion. Nothing carrying information, energy, or mass can exceed it. Yet, despite this strong foundation, scientists and thinkers have never stopped asking whether this limit is truly absolute or whether it might be bypassed in some deeper or more complex way. This curiosity has given rise to some of the most fascinating and speculative ideas in modern physics. These ideas explore the possibility of faster-than-light phenomena, not by ignoring the laws of physics, but by attempting to work within or extend them in unusual ways. They include concepts such as tachyons, wormholes, and warp drives. While none of these ideas have been proven to exist, they continue to challenge our understanding of space-time and inspire new ways of thinking about the universe. One of the earliest theoretical ideas involving faster-than-light motion is the concept of tachyons. Tachyons are hypothetical particles that, if they exist, would always move faster than light. Unlike ordinary particles, which slow down as they gain mass and energy, tachyons would behave in the opposite way. They could never slow down to light speed or below it. Instead, they would always remain in the superluminal range. The idea of tachyons arises naturally in some mathematical formulations of relativistic physics. However, their existence leads to serious conceptual problems. If tachyons could carry information, they could potentially violate causality, allowing effects to occur before their causes in some reference frames. This would create paradoxes that break the logical structure of physical law. Because of these issues, most physicists believe tachyons are not physical particles, but mathematical artifacts that indicate instability or limitations in a theory. No experimental evidence for tachyons has ever been found, and their role in physics remains purely speculative. A more widely discussed idea in theoretical physics is the concept of wormholes. Wormholes are hypothetical structures in space-time that act as shortcuts between distant regions of the universe. Instead of traveling through normal space, an object entering a wormhole could theoretically emerge at a faraway location almost instantly. In principle, wormholes arise as solutions to the equations of general relativity. These equations allow space-time to bend and curve in extreme ways under the influence of gravity. In some cases, this curvature can form a bridge connecting two separate points in space-time. If such a structure could exist and remain stable, it would provide a form of faster-than-light travel, not by exceeding the speed of light locally, but by reducing the distance between two points through space-time geometry. In this sense, The travel would still respect the speed of light limit within local regions, but the overall journey would appear instantaneous or near instantaneous. However, wormholes face significant theoretical challenges. Most solutions suggest that they would collapse almost immediately unless held open by some form of exotic matter with negative energy density. Such matter has not been observed in the required quantities, and it is unclear whether it can exist in stable forms. Even if stable wormholes were possible, they would introduce additional problems related to causality. Depending on how they are used, wormholes could potentially allow information to be sent into the past, creating time travel paradoxes. This raises deep questions about whether the laws of physics permit such structures at all. Another speculative idea is the warp-drive concept, most famously associated with the Alcubierre metric. This theoretical model suggests that instead of moving a spacecraft through space faster than light, one could distort space itself. In this scenario, space in front of the spacecraft would contract while space behind it would expand, effectively carrying the spacecraft forward. From the perspective of the spacecraft, it would remain locally stationary within a bubble of space-time. However, the bubble itself would move through space at an effective speed greater than light. In this way, the speed of light limit is not violated locally, because nothing inside the bubble exceeds light speed relative to its immediate surroundings. The idea is mathematically consistent within general relativity, but it requires conditions that are far beyond current technological capabilities. Like wormholes, it appears to require exotic forms of negative energy or matter with unusual properties that have not been observed in sufficient quantities. Even more importantly, there are concerns about stability and control. It is not clear whether a warp bubble could be created, maintained, or safely directed. Some studies also suggest that high-energy radiation could accumulate at the edges of such a bubble, making it potentially destructive. Despite these challenges, warp-drive concepts remain an active area of theoretical research. They push the boundaries of how we understand space-time and challenge the assumption that the speed of light limit is always tied to motion through space rather than the structure of space itself. Another area of interest involves quantum entanglement. When two particles become entangled, their properties become correlated in such a way that measuring one instantly determines the state of the other, regardless of distance. This seems to suggest a kind of instantaneous connection between distant points. At first glance, this appears to violate the speed of light limit. However, closer analysis shows that entanglement cannot be used to transmit information faster than light. The correlations are instantaneous, but they are random and cannot be controlled to send meaningful signals. This preserves causality and ensures that relativity remains intact. Even though entanglement appears to involve non-local connections, it does not allow faster-than-light communication. Instead, it reveals a deeper level of structure in quantum systems that is not yet fully understood. Some interpretations of quantum mechanics suggest that entanglement reflects a more fundamental non-local structure of reality. In these views, space-time and locality may emerge from deeper quantum relationships rather than being fundamental themselves. If true, this could reshape our understanding of space, time, and information. There are also more subtle ways in which faster-than-light effects appear in physics without violating relativity. For example, in certain media, light can appear to travel faster than its usual speed in vacuum due to changes in how waves propagate. However, these effects do not carry information faster than light in vacuum and do not violate the fundamental limit. Similarly, phase velocity and group velocity in wave physics can sometimes exceed the speed of light, but again, this does not allow for faster-than-light transmission of information. The underlying signal speed remains constrained by relativity. These examples highlight an important point. The speed of light limit is not just about how fast something appears to move. It is about how information and causality propagate through space-time. Any apparent violation must be carefully examined to ensure that it does not actually break this deeper rule. Even though all known physical evidence supports the speed of light as an absolute limit, the continued exploration of these ideas serves an important role in physics. They help test the boundaries of existing theories and reveal where our understanding may be incomplete. For example, studying hypothetical constructs like wormholes and warp drives has led to deeper insights into general relativity, quantum field theory, and the nature of space-time energy conditions. Even if these structures do not exist in reality, the mathematics behind them helps refine our understanding of what is physically possible. There is also a philosophical dimension to these ideas. The existence of a universal speed limit raises questions about whether the universe is fundamentally constrained or whether these limits emerge from deeper principles. If space-time itself has a deeper underlying structure, then the speed of light may be a feature of that structure rather than an arbitrary boundary. Some theories of quantum gravity suggest that space-time may not be continuous at the smallest scales. Instead, it may be composed of discrete units or emerge from more fundamental informational processes. In such frameworks, the speed of light could arise naturally from the way information propagates through this underlying structure. If this is the case, then the speed of light is not just a physical limit, but a reflection of how reality is built at the deepest level. It would represent the maximum rate at which information can be transferred between fundamental units of space-time. This perspective connects faster-than-light speculation to more fundamental questions in physics. Instead of asking whether we can break the speed of light, we begin to ask why this limit exists in the first place and what it tells us about the nature of reality. Despite the imaginative possibilities, every confirmed observation so far reinforces the same conclusion. The speed of light remains the ultimate speed limit for information and causality in the universe. No experiment has ever demonstrated a violation of this rule. This chapter shows that while faster-than-light ideas are intriguing and mathematically rich, they remain speculative. They challenge our intuition and push the boundaries of theoretical physics, but they also highlight the strength and consistency of the speed of light as a foundational principle. In the end, these concepts do not weaken the idea of the light speed limit. Instead, they deepen our understanding of why it exists and how deeply it is woven into the fabric of space-time. Across the entire structure of modern physics, there is one constant that appears again and again: shaping every layer of reality from the smallest particles to the largest structures in the universe. It is not a force, not a substance, and not a single object. It is a limit. The speed of light defines how fast information can travel, how space and time relate to each other, and how causality itself is preserved. In this final chapter, we bring together everything that has been explored and look at what this limit truly represents for our understanding of existence. At first glance, the speed of light seems like a simple measurement. It is a number that describes how fast light travels in a vacuum. But as we have seen throughout this exploration, that number is not just a property of light, it is a property of the universe itself. It is embedded in the equations that describe motion, energy, gravity, and quantum behavior. It is not something light carries, it is something light reveals. To understand its deeper meaning, we must first recognize how unusual it is that such a limit exists at all. In everyday experience, limits are often practical. A car has a maximum speed because of engine power, friction, and mechanical design. An airplane has a limit because of air resistance and structural strength. But these are not fundamental limits. They can, in principle, be improved with better technology. The speed of light is different. It is not a limit imposed by materials or engineering. It is a limit embedded in the structure of space-time. No improvement in technology can change it. No increase in energy can overcome it. It is absolute in a way that few other quantities in physics are. This absoluteness becomes clearer when we examine how deeply it is woven into physical law. In relativity, it defines the relationship between space and time. In electromagnetism, it determines how electric and magnetic fields propagate. In quantum field theory, it sets the maximum speed at which interactions can occur. In cosmology, it defines what parts of the universe can be observed and influenced. Every major framework in modern physics depends on it. If the speed of light were different, the entire structure of physical law would change. Atoms might not form in the same way. Stars might not ignite. Galaxies might not evolve into stable structures. Even the possibility of chemistry, and therefore life, depends on the balance created by this constant. One of the most profound consequences of the speed of light is that it unifies space and time into a single framework. Before relativity, space and time were considered separate and absolute. Space was the stage on which events occurred, and time was a universal flow experienced equally by all observers. Relativity changed this view completely. It showed that space and time are not independent. Instead, they form a unified structure called space-time. The speed of light acts as the conversion factor between space and time, linking them into a single geometric framework. This means that motion through space affects motion through time. The faster an object moves through space, the more slowly it moves through time relative to other observers. At the extreme limit, as motion approaches the speed of light, time dilation becomes so strong that time effectively slows to zero for massless particles. This relationship reveals something profound. Time is not a universal background. It is part of a dynamic structure that depends on motion and perspective. The speed of light is what holds this structure together. Another key insight is that the speed of light defines causality. It determines what can influence what and in what order events can occur. Without this limit, the universe would lose its logical structure. Effects could occur before causes, and information could loop in contradictory ways. The light cone structure of space-time ensures that causality is preserved. Every event has a region of influence defined by the speed of light. Within this region, cause and effect relationships are possible. Outside of it, events are disconnected and cannot interact. This structure creates a universe that is ordered and predictable. It ensures that the laws of physics remain consistent across all reference frames. It also ensures that information flows in a controlled way, preventing paradoxes that would otherwise arise from unrestricted communication. The speed of light also defines the limits of observation. Because information takes time to travel, everything we observe is a reflection of the past. The farther we look into space, the further back in time we see. This turns the universe into a layered structure of history where distance and time are inseparably linked. This observational delay is not a flaw in our perception. It is a fundamental feature of reality. It means that the universe is never seen directly as it is in a global present moment. Instead, it is reconstructed from signals that have traveled across time and space. This leads to an important realization. Our understanding of the universe is always incomplete and delayed. There is no way to access the entire universe instantaneously. Everything we know is filtered through the finite speed of light. Yet this limitation is also what makes science possible. Because light travels at a constant and finite speed, we can reconstruct distances, motions, and histories in a consistent way. If light traveled instantaneously, or if there were no speed limit, the structure of observation would collapse into chaos. The speed of light also shapes the evolution of the universe itself. As the universe expands, distant regions move apart, and the light traveling between them becomes stretched. This stretching leads to redshift, which allows us to measure cosmic expansion and understand the history of the universe. Over time, this expansion creates horizons that limit what can be observed. Some regions of the universe are moving away so quickly that their light will never reach us. Others are already beyond our observational reach. These cosmic horizons define the boundary between what is accessible and what is forever hidden. This means that the universe is not fully open to observation. It is divided into regions of visibility and invisibility, shaped by the speed of light and the expansion of space. Our cosmic perspective is therefore always local, even though the universe itself may be far larger. Despite these limitations, the speed of light also provides coherence. It ensures that physical laws are consistent across space and time. It allows different regions of the universe to evolve according to the same principles, even if they are no longer in contact. This consistency is essential for the formation of structure in the universe. Without it, stars, galaxies, and planets might not form in a stable way. The speed of light helps maintain the uniformity needed for complexity to emerge. It also plays a critical role in energy and matter. The relationship between mass and energy, expressed through the equation E equals mc squared, shows that mass itself is a concentrated form of energy. The speed of light squared acts as the conversion factor that determines how much energy is contained in a given amount of mass. This relationship explains the immense energy released in nuclear reactions and the energy processes that power stars. It shows that even small amounts of matter contain vast reservoirs of energy, all governed by the structure of space-time. In the quantum world, the speed of light ensures that interactions remain consistent with relativity. Even though quantum phenomena can appear non-local or probabilistic, they still respect the causal structure defined by light speed. Information cannot be transmitted faster than this limit, preserving the integrity of physical law. Across all scales, from quantum fields to cosmic expansion, the speed of light remains a unifying principle. It connects different areas of physics into a coherent framework. It is not just one constant among many. It is the constant that defines how others relate. This raises a deeper question. Why does this limit exist at all? Is it simply a property of our universe, or does it reflect something more fundamental about reality itself? Some modern theories suggest that space-time may not be fundamental. Instead, it may emerge from more basic structures, possibly related to quantum information or underlying computational rules. In such models, the speed of light could emerge naturally as the maximum rate at which information can propagate through this deeper structure. If this is true, then the speed of light is not just a feature of space-time. It is a reflection of how reality processes information at the most fundamental level. It would represent the ultimate speed at which the universe can update itself. Even without a complete theory of quantum gravity, the evidence we have consistently supports the idea that the speed of light is deeply rooted in the fabric of reality. Every experiment confirms its invariance. Every observation depends on it. Every theory incorporates it. In the end, the speed of light is more than a physical limit. It is a defining principle of existence. It determines how the universe is seen, how it evolves, and how it can be understood. It shapes the relationship between space, time, energy, and information. It is the boundary between the possible and the impossible in physical terms. It is the rule that ensures the universe remains consistent, ordered, and intelligible. When we look at the night sky, every point of light is a reminder of this limit. Each photon carries a message from the past, traveling across space and time to reach us. Every observation is shaped by this journey. The speed of light is not just a number in an equation. It is the silent framework behind everything we see, everything we measure, and everything we know about the universe. It is the ultimate limit, not because it restricts the universe, but because it defines it.